Hi. Now we are going to do homework question 3. Uh, and another apology here. This question also is very dirty and uh, I don't know, pointless, meaningless. So just dirty algebra homework question. So I'm going to delete it next year. I don't know why I included it last year, and so I wanted to make a question about two-stage estimator, and I made it last year. I forgot to delete it this year. I'm sorry about that. And so the answer is very, very dirty, but let me try this. Excuse me, I did not. I am updating it real time. So in our setup, uh, we have, and following the notation in what we used in class. By the way, like if you are not going to define what is what, like please write something like this, or like you just if you write m equals to this, then so as if you are writing your dissertation, you have to define what is what, and if it's cumbersome, then please cite something like this. Make your answer complete, like self-containing, or if you need to cite something else, you may cite that, uh, right? You know, so this is the moment function for the first stage, and that's derivative is given by this, and then the influence function is given by this. Here, like a common mistake you made here is that writing like this. It's 2 by 1 vector, and it is 2 by 2, and this is 2 by 1. It is scalar. The problem here is it is not true because it is 2 by 2. It's scalar, scalar. 2 by 2, 1 by 1 does not match. You cannot calculate this. So this is where the difficulty arises. I think when I make this question, I thought this is how we get, and that was my mistake. So the problem, the reason why the question is that complicated is because you have to calculate the matrix inverse M. That's a problem. However, let me show you on like anyhow. If you follow the notation in the lecture note, you can easily obtain the results. This is wrong, but if you calculate this inverse, then element-wise, you can get phi1 and phi2. That's dirty algebra, but let me show you an alternative way to handle this question. And I did not do it in I did not do it carefully in class, so let me use this as a chance to show you what is going on. Here it is simple OLS formula, and so we regress x2 on z, z1, z2, and then you may replace x2 using its true regression equation. True equation follows this form. So as a result, gamma 0 is isolated, and then psi, the error term, determines the random error, the error in the estimator. So that is gamma hat minus gamma 0 is something depend on psi. But what we are going to do here is, we know this inverse, this guy inverse will converge in probability to this, right? So this plus an error term that converges in probability to 0. This is the notation for that. And then as a result, we have, you can use it as a kind of just a usual term. So you have this times this and this times this. And this is what we want usually. And we know this will converge to 0. What we want to do here is we want to show that this converges to 0 fast enough. Fast enough means this, right? It goes to 0 faster than 1 over square root n, right? That means this term, even if you multiply square root n, this term should go to 0. And how do we... And then if you have that, then we have this form which satisfies the definition of influence function. And I find a typo in the lecture note here. Here I multiply square root n here, and also I multiply square root n here. Then I had to multiply square root n here. It should be square root n. So it's another typo, another error in this question. Here typo. Two typos. Sorry about that. I'm going to delete it. I'm going to update that question next year. So anyhow, then how do we prove this equation, this equality? That is easy, because we just want to show that if you multiply square root n to this part, it should be bounded. Bounded in probability. And that is given by the central limit theorem. If you multiply square root n to this term, then we know it converges to a normal distribution, so it is bounded in probability. So bounded in probability and converge to 0 in probability, combined converges in probability. So something like this. What we want to do here is suppose that an is bn times cn. These are random variables depending on n, and we want to show that the multiplication converges to 0 in probability faster than 1 over square root n. That means even if you multiply square root n, it has to converge to 0. We need to show this, and what we are going to do here is b converges to 0 in probability. All right, it is obvious in this case, because we already have this, and we want to show that this, if you multiply square root n to c, it does not diverge. So it's bounded in probability, right? Then we have the desired result, because something does not diverge multiplied by something goes to 0 will converge to 0, right? So in this case, C equals to this guy, which follows the central limit theorem. So after multiplying square root n, so multiply square root n times C converges in distribution to a normal distribution. So it does not diverge. So we get the desired result. So this is an easier way to understand the influence function. So in this case, actually, it's too simple. So you don't need to derive the influence function here. But as you see in this question, the influence function is to show which component is affecting the final result how much. So we want to decompose the final standard errors, decompose that into the error coming from the first stage estimator, or intrinsic error, or blah blah blah. So let's have a look. I'm going to define a new set of notation. Sorry about complicatedness. So here I had to say comma hat, right? So what I'm doing here is just W is just a generic gamma. For a given gamma, we define W, and W hat is for gamma hat. It's typo. And W tilde is for the true value of gamma. So if you know the true value of gamma, you don't need to estimate the first stage, but you may simply utilize W tilde. But of course, in our actual implementation, we have to use W hat. And then we know for n, and also what's important here is W is a function of gamma, because we are going to differentiate the function, and then you have to consider this. And we have moment condition this way, and that means moment condition, it looks like moment condition has two arguments, but actually not. Gamma is not an argument. Like you may think it as a preliminary, like we usually call it a nuisance parameter. So that it, like the meaning of this function is that if gamma is given, correctly given, then this as a function of beta, it is satisfied only at beta 0. That's the meaning. So gamma should be given. So to evaluate the moment function, gamma should be given and gamma does not play any role. So it's true only when gamma is true and beta is true. And again, following the lecture note, we have the result like this. So phi1 is the influence function from the first stage, and this is this is g is the moment, and multiplied by something. And what we need to do here is we just need to calculate these guys. So you have to differentiate this guy with respect to first beta. If you differentiate with respect to beta, and evaluate it at beta 0 and gamma 0. So using gamma 0, because gamma equals to gamma 0, it becomes W tilde. So this step is pretty simple. But like gamma, if you differentiate with respect to gamma, the problem here is gamma is here and gamma is here. You have to differentiate with respect to each of them, both of them, and then you get, so if you differentiate with respect to the first gamma, you get this. And if you differentiate here, then you get this, right? That is what you get. And the first term disappears because when you evaluate at beta 0 and gamma 0, these guys equal to this error term, and we know it's exogenous, so it becomes 0. So this part goes away and only have the second part, which is pretty similar to the usual algebra. Okay, and as a result, if you plug in, you can derive the effect of influence function on the second stage estimator, but that's really annoying. That's annoying. You can do that, but like you have to calculate the inverse function. Very annoying. I'm going to skip that. And here again, as a bonus, I'm going to show you an alternative way, maybe a more intuitive way to understand this problem. So now what we are going to do here is we are going to define error term u a little bit differently. So this u includes second stage error term and first stage error term and additional error term. So in the fitted value approach, we considered this, right? But now we have additional randomness coming from the random error in the first stage estimator. That is a new component. And then what we can do here is like y, and this is what we did in the identification chapter. We did it this way. But actually, in practice, we do not observe gamma 0. So you have to replace gamma hat and add and subtract this additional term. So because of this additional term, we have this additional error term, right? And then you can write it as W hat. So then we are going to use this to derive. It's complicated, not much complicated. So follow the same rule, like it's like OLS. This is OLS. Beta hat is calculated as an OLS estimator, and y is now replaced by the previous here W hat. Sorry again, should be W hat. W hat beta 0 plus u, and this beta 0, like here W hat. So we'll go outside of the complicated formula, and u should be replaced by this longer 3 different error terms, right? 3 different error terms, and this part is not a problem. These guys are intrinsic errors. Like that is, even if you know the true value of gamma 0, or if you know the true fitted value, still you will have this much error. These error terms are not going anywhere, right? So, however, we are looking at this guy, the additional effect of the additional error term. This additional error term can be written in this way, and again, under suitable conditions, we know this guy converges to some error, this guy converges, and this guy converges, this guy converges. So each term, like, because gamma hat converges to gamma 0, so W hat should behave accordingly. And so this guy, this guy, this guy are following these rules, which is pretty straightforward, even though it's not a complete proof. But I believe you can show that using the previous like results. And then now we are going to study this guy. This guy is slightly different. We have to show that this converges to this guy. So the difference is W hat and W tilde, but the error term residual should be converging to 0 faster than 1 over square root n. That is a problem. So this is slightly different, and this is because an influence function should have error term smaller than, like quicker, like converging faster than 1 over square root n. So this should be proven, but it's not that difficult, because if you subtract these two terms, then you get this, and this is basically gamma hat minus gamma 0 times z, right? So this guy follows the center limit theorem as before, and this guy is OP1, small OP1. So same result applies again here. And then as a result, we have proved this. And then combining all the results, so remember this formula. So beta hat minus beta 0 equals these guys. Complicated guys. And we copy them. Oh my. Haha. Yeah, this is what we have. And we know this guy converges to this plus small p1. And this converges to this plus small p 1 over square root n. This converges to this plus small p1. And this converges to this plus small p1. So plug in everything. And then in the end, what we have is a very nice thing. Like this. So this is the original influence function, intrinsic influence function, even if the first stage has no error. And the second part is the error influence coming from the first stage, right? So we are interested in this guy. And this guy is so the effect of the first stage estimator is captured by this coefficient. The coefficient is a matrix. So minus beta 2 times something inverse times something. So this is the effect of the first stage estimator. And this equals to the formula we derived in the lecture note. Right? We derived ahead earlier. So if you, I think this is a better way to explain the idea of effect of the first stage on the second stage. So I hope, I'm sorry about the dirty and pointless question, and this is I hope you understand it better by trying the question. Okay.